Hi everyone, today I'm going to present our final project, graph modeling strategy for topic discovering in global news using finalProject. The main goal of this project is to explore how different graph modeling strategies affect topic discovery in news data. Instead of only building a finalProject demo, we designed this project as a data science experiment. We collect global news article titles, extract named entities, build knowledge graph in finalProject, and compare different graph structure using community detection. The key question we want to answer is, if we model the same news entities in different graph structure, will the detected topic become different? There are three main things you can learn. First, you can learn how to construct a simple knowledge graph from news data. We start from unstructured news title, extract entities such as company, people, countries, and products, and then store these entities and relationships in your project. Second, you can learn the trade-off between different graph modeling strategies. In this project, we compare a raw co-occurrence graph and the filter weight graph. The raw graph keeps more relationships, while the filter graph moves with or noisy relationships. Third, you can learn how graph-based community detection can help with topic discovery. We use Ruben and label propagation to group relation entities into community, and then interrupt this community using topic entities with case study. The important idea is the graph constructor is not neutral. The way we build the graph affects what kind of topic we can discover. The whole flow discloses data collection, data preprocessing, feature extracting, transformation, feature selection, as explained design, and result and analysis. For data collection, we use UDELT article list to collect global news article metadata. For data preprocessing, we clean the article titles. For feature extracting, we use name entity recognition to extract entities from the titles. For transformation, we transform text data into graph data in project. For feature selection, we apply entity filtering and graph-ready entity selection. Finally, for experiment design and result analysis, we compare different graph models and analyze their community detection results. The main focus of this project is on experiment design and the result analysis. This is because our main contribution is not just collecting data, but comparing G2 and G graph, modeling strategy, and explaining the difference. News articles are usually unstructured text. So first problem is the entities relationships are hidden in text. The second problem is the named entity recognition is not perfect. Since we are working with technology news titles, some terms can be misclassified. For example, a general-purpose NER model may classify NVIDIA as a location or classify GPU as a person. Therefore, our project asks three research questions. First, does graph modeling strategy affect community detection? Second, can a filtering graph improve interpretability? Third, can your project help explain entity relationship? This question guides the rest of the experiments. For datasets, we use GDELT article list. It is a global news data source. However, we didn't download the full dataset because they will be too large for this project. The keywords include artificial intelligence, OpenAI, NVIDIA, semiconductor, TSMC, and US-China technology. After collection and deduplication, we obtain this number news article and 288 different domains. One important limitation is that our collected data mainly contains article titles. The text field was empty in our datasets. So the entity extraction was mainly based on new title rather than for article 10 contents. This is a limitation, but it's still enough for our goal because our focus is to compare graph modeling strategy, not to perform for news article understanding. After collecting the news title, we use name entity recognition or NER to extract entities. In this project, NER means identifying name entities such as companies, people, countries, location, and products. We use space as a tool to perform NER. However, space is a general-purpose NER model. It's not specification trained for AI or semiconductor news. Because of that, it sometimes misclassify technology terms. To improve entity quality, we add several cleaning steps. We use stop list to remove noise title fragments. We use align normalization to merge difficult names such as US, UDAS, and United States. We also use type override to correct important entities such as setting NVIDIA or ORG and the GPU as products. After filtering, we generate graph-ready entities. The final graph-ready dataset contains 206 entity mentioned and 92 unique graph-ready entities. This step is very important because noise entities will directly affect the quality of the graph and the community detection results. The first graph is G1. The artificial entity graph. The article entity graph. In G1, each article is connected to the entities mentioned in its title. And the second graph is G2, the raw entity co-occurrence graph. G2 is derived from G1. If two entities appear in the same article title, we connect them with a co-occurrence with relationship. If the same pair appears in multiple titles, the weight of their relationship increase. The third graph is G3. The filtering weight entity graph. G3 is created from G2 by filtering ages. It keeps stronger or more reliable entity relationship and removes weak or noise ones. So the relationship among these graphs is G1 is the foundation graph, G2 is an entity projection from G1, G3 is filtering subset of G2 edges. This design allows us to compare how different graph structure after topical discovery. We can see G2 has 116 projected edges, while G2 has 64 projected edges. And G2 keeps all graph-ready co-occurrence relationship, while G3 removes low weight or subspecial relationship. This reduction is expected. G3 is designed to be more selective. In other words, G2 is give us a denser graph, but it may include more noise. G3 gives us a sparser graph, but the remaining relationships are expected to be cleaner and easier to explain. So lower edge count doesn't mean G3 is worse. It means G3 trade graph density for better interpretability. We use Neo4j graph data science to run Leuven and label propagation. We didn't implement Leuven from scratch. Instead, we built a graph in Neo4j and call the Neo4j GDS Leuven procedure. Leuven is a community detection algorithm. It groups strongly connects entities together by optimizing the metric called modularity. Our results show that G2 has 33 communities, and the majority score is this. And at first glance, G2 seems better because it has higher majority, but we shouldn't interrupt the way directly. It has more edge, so the graph is denser, and the community are easier to form. G2 removes many weak edges, so the graph becomes more fragmented. This is why G2 has more community and lower modularity. Therefore, modularity alone is not enough. We also need qualitative interpretation and case study. After community detection, the algorithm only grabs us community ideas. For example, it may output community 1, community 2, and so on. However, these numbers don't tell us what the community means. To make the result interpretable, we look at the topic entities in each community and assign rule-based topic label. For example, if a community contains NVIDIA, Jason Huang, TSMC, Taiwan GPU or CPU, we label it as AI and semiconductor supply chain. If a community contains Elon Musk, Sam Altman, OpenAI, or ChatGPT, we label it as AI leader or generative AI. Most communities are labeled as other and unclear. This doesn't mean they are useless. It means their topic entities are too small, too mixed, or don't clearly match our predefined rules. Also, these labels are not group truth annotation. They are our interpretation for qualitative analysis. This step helps us connect numerical community detection results with human understandable topic. We select NVIDIA because it's a central interest in AI and semiconductor news. In the GIS-driven results, NVIDIA is connected to China. Jason Huang, CPU, Taiwan, and list. These relations are meaningful. NVIDIA and China reflect the connection between AI chips and geopolitical technology competition. And this entirely from a topic they can be interpreted as AI and the semiconductor supply chain. This case study shows the value of graph modeling. Instead of looking at isolated keywords, we can see how companies, people, products, and countries are connected in the new graph. There are two main observations in this project. First, G2 and G3 show a clear trade-off. G2 is denser and has higher modularity, but it may include more low-weight or noisy relationships. G3 is sparser and has lower modularity, but its key relationships are cleaner and easier to explain. Second, graph modeling strategy matter. Even with the same entity set, changing the edge construction may change the community detection results. There are also some limitations. First, our dataset mainly contain article titles, not fully article text. This limits the number of extract entities. Second, space NR can misclassify technology terms and title fragments. We reduce this problem with entity filtering, but it cannot be completely removed. Third, our topic labels are rule-based interpretation, not script truth label. So we don't claim that G3 is always better. Instead, we show that different graph models provide different types of insights. To conclusion, this project shows that graph modeling strategy doesn't affect community detection in a new knowledge graph. And overall, Neo4j is useful not only for storing graph data, but also for querying, comparing, and explaining entitled relationships in news data. Thank you for listening.